Every year, over 40 billion coins are minted worldwide. But you'll never guess where it all begins. Imagine giant rolls of metal weighing 8,000 pounds, entering a workshop like armored trains. There, something incredible awaits them. Presses that strike with a force of 200 tons, and furnaces that heat up to over 1,200 degrees Fahrenheit. Every strike is a new story in your pocket. But there's one thing they don't show in any documentary film. And if you watch this video until the end, you'll be the first to find out. The whole show begins not with a shine, but with the dull scrape of metal, as huge coils, resembling giant toilet paper rolls, are brought into the workshop. Only this isn't cellulose, it's copper, zinc, nickel, or special alloys. These rolls are called coinage coils, and they look serious. Each coil weighs up to 8,000 pounds and is up to 13 inches wide, depending on the type of coin. The metal strip is slowly unwound, like a giant snake, and fed into a straightener, a system of rollers that removes waves, bends, and misalignments. Because precision is sacred, even a tiny bend of 1/100th of an inch can ruin the subsequent stamping. The strip thickness is up to 0.125 inches, and this thickness is controlled in real time by sensors, lasers, and automation. Everything is precise because otherwise the blanking press would simply fail or start making crooked blanks. Each metal is for its own denomination. Zinc strips with copper plating, for pennies. Copper-nickel alloys, for nickels, dimes, and quarters. Bronze alloys with manganese, for $1 coins, like the Sacagawea or US presidential coins. These rolls are not only heavy, they are also expensive. Every centimeter must be used wisely. Therefore, the metal also undergoes an automatic inspection for dents, cracks, and residual oxides. Defects are rejected immediately, cut off, and the strip moves on, like a well-sharpened knife. Next, it faces a press battle. But already here, in the preparatory stage, the fate of each future coin is shaped. Because if the strip isn't made perfectly, there will be no George Washington, no Abraham Lincoln. There will be scrap metal. After the metal strip is straightened, leveled, and approved, it slowly but surely enters the zone where its main trial awaits, the blanking press. And if you think this is some boring little press, then throw that thought out right now. This machine is a metal beast, a hydraulic monster that pounds the metal so fast that the human eye can't blink between strikes. These presses don't just cut out circles, they slam into the strip at a speed of up to 750 strokes per minute. Bam, 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 bam. It's like a mixer on steroids collided with a military ram. Inside, dozens of high-precision dies, similar to cookie cutters, only this isn't cookie dough. It's copper, zinc, nickel, bronze. And when they come down, perfectly round metal blanks fly out of the strip, which has been heated to a shine. Their diameter is clearly defined. These are the embryos of future money. They are still without portraits, without inscriptions, without shine, dull, matte, sometimes with burrs on the edges, but already with the right size, weight, and character. And now imagine the scale. One press can cut up to 14 blanks every second, or 800 to 1,000 pieces per minute. In a day, millions of circles. And this is just on one line. And there are dozens of such lines in the mint. When the die strikes, a dozen or two circles are cut from the strip with each blow, and the leftover metal, meaning everything between the circles, is instantly rewound, wound onto another coil, and sent for recycling. Nothing is wasted. Here, you know, money is even in the scraps. The blanks fly out onto a conveyor belt, hot, slightly discolored, with a light trace of oil and dust. They are collected in metal boxes, sometimes even poured like grain, straight from a chute. Clink, clink, clink. And this sound is simply hypnotizing. A metal rain of future coins. The air is thick with dust and lubricating vapors, smells of metal and money. Literally. Did you smell it too? So you've seen how circles are cut from dull metal, but that's not all. They are still raw, matte, a bit dirty, with oily marks from the press. They need a real spa day. So the first stage is washing. The circles are loaded into huge vertical drums that resemble washing machines, only the size of a bathtub. Inside, hot water around 140 degrees Fahrenheit with an acid solution and special detergents. The drum spins. The circles bang against each other like a foamy dance of metal balls. Everything is removed. Dust, oil, traces of oxides. The water hisses, steams. After this, drying. The drum tumbles the circles, drying them with hot air so that not a single drop remains on the surface. Wet blanks are death for stamping. Next, a real fire ritual, the annealing furnace. These metal circles race through a long furnace, 12 to 40 feet long, where the temperature reaches a crazy 1,250 degrees Fahrenheit. The metal becomes red hot, but doesn't melt. It softens. It's like warming up the body before hard work, so you don't tear a muscle. After the furnace comes rapid cooling. The circles fall into a bath of cold water, about 50 degrees Fahrenheit. This temperature shock makes the metal stronger and more elastic. Then the circles are coated with a thin layer of graphite lubricant, so that during stamping, the press doesn't stick or scratch the surface. This is the final cycle of drying and preparation. Now they are shiny, flexible, and ready to take on a pressure of 400,000 pounds per square inch during stamping. From washing and baking, the circles are no longer just pieces of metal. They are real contenders for the role of a coin. But all they have now are clean, smooth discs, without faces, letters, or shine. And now it's time to give them character, a soul, and a history. The tool for this is the coining press. A huge steel machine stands like a rock in the hall, with a mechanism capable of pressing with a force of up to 200 tons. It presses so hard that sparks don't fly from it, but the metal on the circle sinters and takes shape with incredible precision. When a circle enters the press, it is clamped between two dies, an upper and a lower one. Each die, like a carved hammer, imprints all the details into the metal. Portraits of presidents, coats of arms, dates, inscriptions, fine lines, and even the smallest letters. All this is incredible microwork, executed with surgical precision. In an instant, the press strikes the circle with insane power, and the metal from fine grains turns into a pattern that thousands of people will see in their pockets and wallets. And it's not just one strike. Some machines have double-sided stamping, where both the obverse and reverse are applied at once, all in a fraction of a second. The speed is impressive. One machine shoots out 750 coins per minute, and dozens of such presses work simultaneously in the workshops, so tens of millions of coins are produced in a day. It's like music, only instead of drums, it strikes on metal, and instead of a melody, a chain of shine and power. After stamping, the coins don't shine right away. They are still warm, and may have small burrs. Next on the conveyor, the coins move to inspection machines. Laser sensors determine the exact diameter and thickness. Visual cameras search for defects in the relief and surface. The human hand is still necessary for rejecting flawed specimens. And so, the coin has passed through all the infernal stages, from the hot furnace to the press strike, and is now ready for its grand debut into the real world. But before that, a final march through the packaging area. Coins come off the conveyor, clinking, flashing, rustling. They are no longer counted individually. They are counted by weight. They are poured into special metal bags or large containers, similar to coffee bags, only each one holds up to 4,000 coins. For example, a standard bag of quarters is $1,000, and the weight of such a package is about 60 pounds. Impressive, right? When a bag is filled, it is hermetically sealed. A seal and a barcode are applied. Next, onto a pallet with hundreds of its brethren. All this into huge trucks that deliver money across the country. To banks, ATMs, stores, soda machines, the military, wherever. And sometimes they are packaged in rolls, small paper tubes. These are for retail circulation. They pour into boxes, clicking like casino chips, and you can already hear them clinking in someone's cash register. This is how an everyday miracle is born. You drop a coin into a parking meter, and behind it is a whole story from a hot workshop, fire, hydraulics, and people who give metal life. Imagine this: red-hot metal up to 33 feet long, bending as easily as if it were a sheet of paper. Every year, factories all over the world create millions of parts, from car bodies to giant pipes, thanks to bending machines. But how are perfect bends, channels, and even spiral shapes for oil and gas giants born from cold, formless steel? And how can it be done without wasting tons of energy? Let's dive into a world where metal obeys human will. A bending machine. Think of it like a big construction set for metal. Imagine a flat sheet that needs to be bent into a specific shape. The machine takes this sheet and bends it using special tools to get the desired angle or form. First things first, the metal sheet needs to be checked to make sure it's suitable for the required part. This includes checking dimensions and looking for defects like cracks or breaks. The metal sheet is cleaned of dirt and rust using a wire brush or sandpaper. This is necessary to ensure clear marking and subsequent processing. Markings are applied to the sheet using special tools like rulers, squares, and scribers. The layout includes drawing center lines and contour lines, as well as marking the centers for any future holes in the part. To make sure the markings are clear and don't rub off during processing, the metal surface is coated with a special paint. Dry chalk, a chalk solution with glue, or a copper sulfate solution might be used. After applying the markings, they are checked against the part drawing. In large industrial settings, automated systems are often used to lift and place metal sheets onto the machine. These systems might include conveyor lines and robotic arms that precisely position the metal sheet on the machine's bottom die. In smaller workshops, or during small batch production, metal sheets might be placed manually by workers. Workers in protective suits and gloves lift the sheets using special tools or lifting equipment and place them onto the machine. Metal sheets can vary greatly in size, from small ones easily lifted by hand to enormous ones requiring special lifting equipment. In large industrial settings, you might see sheets up to 33 feet long and up to 10 feet wide. Then, the necessary tools are selected: a punch for the upper part and a die for the lower part. These determine exactly how the metal will bend. During the sheet metal bending process, the machine presses the punch onto the sheet and it bends into the die, forming the required shape. This process allows for creating various shapes and angles, depending on the type of punch and die used. The most common method is V-bending, which is used to create angles of various degrees. This shape is widely used in manufacturing elements for construction, machine, and equipment housings, frames, and so forth. U-bending is used to create U-shaped channels from steel and other metals. This shape is ideal for manufacturing metal profiles and channels. Radius bending is used to make parts with cylindrical or conical configurations. Such shapes are used in the production of pipes, cylinders, and other three-dimensional structures. One variation of polygonal bending used to obtain complex shapes is P-bending. Bending sheet metal allows for creating various shapes and angles, but creating a spiral shape is a more complex process. Spiral forms are usually made using special methods and equipment, such as roll-forming machines. These machines are used to produce cylindrical, conical, and other curved surfaces. They allow for creating spiral shapes by sequentially passing the metal through rollers that gradually form the desired shape. Such machines are widely used in the production of pipes, cylinders, and other metal structures that require a spiral form. While roll-forming machines are operating, you can see how metal sheets pass through the rollers, gradually acquiring the desired spiral shape. Spiral forms are used in various industries and everyday applications. They offer high strength, excellent conductivity, resistance to corrosion, and fatigue. Springs, connectors, heat exchangers, electrical engineering and electronics, the oil and gas industry, chemical processing, and medical instruments. all use products with spiral shapes. For example, in beryllium copper spiral tubing, the spiral form is used in 50% of applications due to its high conductivity and strength. Spiral cables are used in over 70% of industrial automation systems because of their flexibility and resistance to mechanical wear. Spiral springs are found in over 30% of mechanical drives due to their ability to provide varying spring forces. Spiral pipes, often referred to as coiled tubing, offer several advantages in the oil and gas industry. They can easily adapt to changes in elevation and direction during the transport of oil and gas. This is particularly important when constructing pipelines in complex geological conditions. Coiled tubing has a spiral seam, which facilitates installation. This can reduce assembly time compared to traditional pipes with straight seams. Coiled tubing is used in well clean-out technology after hydraulic fracturing. Nitrogen is pumped through these tubes to wash out proppant from fractures, which increases maintenance intervals and reduces the time needed to bring the well back into operation. Metal forms can be made from various materials, such as steel, aluminum, or copper. The choice of material depends on the requirements for the product and the possibility of reuse or recycling. Traditional manufacturing methods can involve high energy and resource consumption, which can negatively impact the environment. However, modern technologies, like using renewable energy sources and optimizing production processes, can significantly reduce this impact. Metal forms can be recycled and reused, which reduces waste and the need for virgin materials. This is especially important for steel and aluminum products. To protect metal structures from corrosion, powder coatings are often used. These are more environmentally friendly compared to traditional paints because they do not contain organic solvents or harmful substances. Switching to solar, wind, or hydropower can reduce greenhouse gas emissions by 70% or even 90% compared to traditional energy sources. Improving technological processes and automation can reduce energy consumption by 20 or 30% and cut waste by 25%. Reusing metal forms reduces waste by 50 or even 70%. Every hour, over 10,000 engines are started worldwide. But what if I told you that behind their operation lies one of the most spectacular, secretive, and precise procedures on the planet? Before you is a huge red-hot cylinder, as long as a bus and weighing as much as a small tank. It will go through the hell of presses, a ritual of grinding down to the micro-inch, and even immersion in boiling oil. This is the story of the creation of a supertanker's heart, a giant crankshaft capable of pushing 400,000 tons through the ocean. But there's one detail that isn't shown in any documentary film. Watch until the end, and you'll find out what exactly makes metal live. For such wonder parts, high-strength alloy steels are used, often with additions of chromium, molybdenum, or vanadium. They provide resistance to fatigue loads and corrosion. The steel must meet strict standards. Its chemical composition, purity, and grain size are checked. This is the heart of the future engine, so there can be no mistakes here. Crankshafts for the most powerful diesel engines are usually forged, not cast as one might think. The reason is a denser metal structure and the absence of voids or cracks. The blank is first heated in a forging furnace to 2,300 degrees Fahrenheit. Then, it is gradually shaped by giant presses that exert a force of over 50,000 psi. A huge steel cylinder, glowing orange-red as long as a bus, weighing under 60,000 pounds. It has just been taken out of the furnace. A wave of hot air emanates from it, forcing workers to keep their distance. The floor underfoot vibrates. The forging begins. This is not a hammer and anvil. This is a hydraulic press as tall as a 2-story building, which, with pressure, slowly and confidently squeezes the perfect shape of the future crankshaft out of the metal. The red-hot block is placed under the press, and with a dull thud, it compresses the steel, changing its structure. Inside, the crystalline lattice melts, becoming denser, stronger, more resistant to future loads. This is just the first strike, then another, and another. Huge manipulator jaws turn the blank at the right angle. It is stretched, bent, compressed, all to form the basic geometry of the shaft: journals, cheeks, counterweights. After several deformations, it is sent back to the furnace. Metal doesn't like to be rushed. If it cools, it becomes brittle. If it overheats, it loses its properties. Nearby, an operator watches every movement through protective glass. Every millimeter matters. A half-inch error can cost thousands of dollars and weeks of rework. On the screen, a temperature map of the part, the press pressure, the feed angle. After just a few cycles, the blank begins to resemble something familiar. It is still far from the finish line, but the shape gradually emerges, a huge skeleton of the future mechanism that will turn the shaft at a speed of 80 revolutions per minute and push the supertanker forward. The supertanker is an incredible 437 yards long. That's almost 4 football fields. After the final strike, the part is slowly pulled aside onto a cooling platform. Steam rises above it, and the crackling of the contracting metal can be heard. Mechanical processing still lies ahead, but already this is a crankshaft blank, the heart of an engine that will feel every wave of the ocean. After all these manipulations, a blank that has been through the hell of forging stands in the workshop, a red-hot steel bone, over 33 feet long, weighing under 25 tons. It already resembles a crankshaft, but only resembles. The surface is all in rough marks from the press. The edges are uneven, and the tolerances are far from precise. And here begins the finest, slowest part: machining. The giant part is carefully installed on a lathe the size of a bowling alley. It is clamped in jaws that can withstand pressures of thousands of psi, and rotation is started. And slowly, carefully, a cutting tool approaches the surface. The metal is turned layer by layer, no more than 0.02 inches at a time, and each of these layers is machined with surgical precision. The lathe is connected to a computer numerical control system, and it forgives no mistakes. Here, thousandths of an inch decide everything, because if the engine's rhythm is uneven, the ship won't be able to hold its course. After rough turning, they move on to milling, forming lubrication holes, making grooves, grinding bearing seats. The tools are coated with diamond dust or made of hard carbide, otherwise they simply wouldn't withstand contact with such dense steel. During processing, the shaft rotates slowly, just 2 or 3 revolutions per minute, sometimes even slower. It is lubricated with a special cooling lubricant, because without it, the tools would overheat and microcracks would appear on the surface. Each surface is checked after a pass with dial indicators and a laser measurement system. No more than 1/1000th of an inch of error. That's the tolerance for the journals that contact the bearings. Everything must be perfectly round, perfectly smooth, perfectly weighted. The crankshaft is a rotating system, and the slightest imbalance in such masses will cause vibration that will tear the engine apart from the inside. Therefore, it is placed on a special stand, sped up, and with the help of high-precision equipment, it is determined where exactly an extra 5 or 6 ounces of steel need to be removed so that the weight is distributed perfectly. After this, final grinding is required. Grinding heads are used to polish the journal surfaces to a shine. Now its dimensions can be measured not in inches, but in micro-inches, because every microscopic defect means overheating, friction, wear. Everything is recorded in a quality certificate, and if something doesn't comply, the blank is sent back to the furnace. This stage takes from several days to several weeks, depending on the shaft's size. But in the end, the output is a perfect steel giant that will rotate in the depths of the engine with a force capable of pushing hundreds of thousands of tons forward. After the crankshaft surface is polished to a shine, a mysterious, almost alchemical stage begins: heat treatment. At first glance, it's already finished, but inside, the metal is not yet what it should be. It needs to be hardened, literally and metaphorically. Because this shaft will work in hell, under loads of tens of thousands of pounds, at temperatures over 300 degrees Fahrenheit, for thousands of hours without rest. The crankshaft is placed in a huge thermal furnace. This is a steel chamber the size of a truck. The temperature gradually rises to 1,500 degrees Fahrenheit, and so the shaft bakes for several hours, sometimes up to a day. This is structure normalization. Upon heating, the steel grains expand, and the stresses that accumulated after forging and machining disappear. The internal metal becomes homogeneous, more elastic, ready for loads. After heating, the part must be hardened. The shaft is taken out and quickly cooled. This can be an oil bath, hot oil in which the steel hisses and bubbles as if boiling, or a controlled flow of air from nozzles. It all depends on the type of steel. But the essence is the same. With rapid cooling, the outer layer becomes super hard, forming a so-called hardened crust capable of resisting wear and friction. But such hardness has a side effect: brittleness. So next, tempering. The shaft is heated again, already to 1,000 degrees Fahrenheit or slightly less, and held for several hours. This restores its balance. The metal remains hard, but no longer brittle. Like a well-tensioned spring. Strong, but elastic. At the end, induction hardening for the most critical zones: the necks and seating areas. They are treated with high-frequency currents. A contour coil surrounds a part of the shaft, creating local heating, followed by instantaneous cooling. This allows strengthening only those areas that receive the greatest loads, without affecting other parts. After the heat treatment is complete, the crankshaft falls into the hands of quality control specialists, and here begins the final, most important act in the creation of this giant part. Not only the engine's operation, but also the safety of the entire vessel depends on the accuracy and reliability of these checks. The first step is a visual inspection. Specialists carefully check the shaft's surface for cracks, scratches, defects in painting or coating. For this, they use magnifying glasses and special lighting devices capable of detecting even the smallest irregularities. After all, any microcrack can become a point of failure during operation. Then, ultrasonic scanners are used, which penetrate deep into the metal and detect internal defects, voids, inclusions, stresses in the structure. The crankshaft is wrapped with special sensors, and a computer system reads the signals and creates a 3D map of its internal structure. Next, magnetic particle inspection. This method allows finding the smallest surface cracks that may be invisible to the naked eye. The crankshaft surface is coated with a magnetic powder, and under the influence of a magnetic field, the powder particles gather at the defect sites, clearly highlighting them. Hey, pull that bottle out of your pantry. Sunflower oil. You see it every time you cook, right? It's just oil. Looks simple. Pour it, heat it, done. But what if I told you that this everyday kitchen staple starts as tiny black seeds and goes through a massive, mind-blowing industrial journey? We're talking about a process of incredible scale, precision engineering, and turning millions of tons of seeds into that clear liquid. Forget your garden patch. Get ready to see the hidden factory secrets behind pure cooking oil. It all begins in the sun-drenched giants of the plant world. Sunflowers. Picture fields that stretch beyond the horizon. Golden faces tracking the sun. These aren't grown just for beauty. They're an industrial crop, covering massive hectares in places like the American Midwest, Eastern Europe, and South America. Contract farmers cultivate them specifically for oil content. When the heavy heads hang low, packed with seeds, specialized harvesters sweep through. These machines are beasts. They rip off the heads, shaking and collecting tons upon tons of seeds in hours. Enough seeds from just one field could fill dozens of semi-trucks. It's harvesting on an epic scale. Once those trucks dump their colossal loads at the processing plant, the real industrial ballet begins. First challenge, cleaning. Seeds from the field come with all sorts of hitchhikers. Dirt, stones, stems, leaves, even metal bits. Contaminants can damage machinery and ruin entire batches of oil. So, the seeds hit a high-speed cleaning gauntlet. They pass over vibrating screens that filter debris, under powerful magnets that yank out metal, and through air classifiers that blow away lighter impurities. The most impressive tech? Optical sorters. Cameras scan every single seed flying by on a conveyor, using light and imaging to spot defects or foreign objects. Precise air jets blast away anything that doesn't belong. They clean millions of seeds per hour, ensuring only pure seeds move forward. This is factory efficiency in action. Clean seeds still have their shells, and the oil is hidden inside the kernel. Next up, hulling. Machines use impact or friction, think high-speed centrifuges or rollers, to crack the tough outer hulls without smashing the valuable kernels inside. It's a delicate balance of force and precision. Then, incredibly clever systems use gravity and air currents to separate the lightweight hulls from the heavier kernels. The hulls aren't wasted. They're often used as fuel for the plant's boilers or processed into animal feed. Maximizing yield means using every part of the seed. Now for the main event, getting that oil out. There are usually two methods. First, mechanical pressing. The kernels are fed into massive screw presses. These are industrial powerhouses. They twist and compress the seeds with enormous force. We're talking pressure equivalent to stacking several elephants on a single spot. Under this immense pressure, the crude oil is literally squeezed out. It flows out in a thick, brownish-yellow stream. This first press extracts a significant portion of the oil, leaving behind a compressed cake of seed material. To extract the maximum amount of oil, especially from the leftover seed cake, a second method is common: solvent extraction. Yes, solvent might sound chemical, but it's a food-grade process, and the solvent is completely removed later. The compressed cake is washed with a specific solvent, like hexane, which dissolves fats. Think of it like a supermagnet pulling out the oil remaining in the material. The mixture of oil and solvent is then heated. The solvent evaporates quickly and is captured for reuse, leaving behind the crude oil. This process gets virtually every drop of oil possible, maximizing efficiency on an industrial scale. After pressing and extraction, you have crude sunflower oil. But it's not the clear, neutral oil you pour in your pan. It's cloudy, has a strong odor, and might contain trace impurities. So, it undergoes refining, a multi-step purification ballet. Degumming removes sticky phosphorus compounds. Bleaching uses natural clays to absorb pigments and make the oil lighter. Then comes deodorization, perhaps the most critical step for a cooking oil. Steam is passed through the hot oil under vacuum, stripping away compounds that cause smells and unwanted flavors. This is what gives the oil its pure, neutral taste and makes it stable, so it doesn't go rancid quickly. The final steps ensure maximum purity and quality. The refined oil goes through polishing filters to remove any last tiny particles, making it perfectly clear. Then, rigorous quality control takes over. Labs at the factory test every single batch. They check for clarity, color, free fatty acids, peroxide value to measure oxidation, and overall stability. This isn't a quick check. It's precise chemical analysis, ensuring the oil meets strict global standards for food safety and quality. Only batches that pass this final gauntlet are approved for packaging. Packaging is the high-speed finale. The pure, refined oil flows to the bottling lines. Empty plastic bottles or glass jars zip along conveyors at incredible speed. They're rapidly filled with precise amounts of oil, capped, sealed, and labeled by automated machines in a blur of motion. A large plant can bottle tens of thousands of units per hour. These finished bottles are automatically packed into boxes, stacked onto pallets by robotic arms, and readied for distribution. From a vast field of seeds to perfectly sealed bottles, it's a journey of transformation driven by engineering and scale. So, the next time you pour that clear, pure sunflower oil, take a moment to think about the complex industrial magic that happened behind the scenes. From countless tiny seeds, through powerful presses, intricate cleaning systems, chemical purification, and high-speed bottling lines, it's a product of massive scale, precision, and technology. It's a fascinating look at how agriculture meets industrial engineering to create something essential for everyday life. What part of this incredible process surprised you the most? Let us know in the comments. Attention! Today we have a very special mission to rescue Private Meat Grinder. This mighty machine makes life easier in countless households, but when it breaks down, a million questions pop up. What do you do with all that metal, plastic, and electronics? Imagine this: nearly 90% of modern meat grinders are made of metal and plastic, which means most of their parts can actually be recycled or reused. There you are, staring down the machine that used to hum happily while turning enemies, meat, into ground perfection. Now you are desperately flipping through the manual, trying to revive what is basically a lifeless pile of parts. Unplug that meat grinder and listen up. You will never know how much you need an electric meat grinder until it breaks and leaves you without one of the most useful kitchen tools. When that day comes, you only have two choices: spend a fortune on a new one, or figure out how to recycle the old one and squeeze some value out of it. Did Baron Karl Drais ever imagine his invention would cause such issues down the line? In the 19th century, he invented a hand-cranked meat grinding machine. Some folks still use these old-school grinders today. Twist the handle, get your ground meat, and work your arm muscles at the same time. But no, you just had to get the fancy electric one. And now you have to figure out how to dispose of it properly. But is there really anything worth saving from an electric meat grinder? It might seem like just another trip to the trash bin, but the truth is, recycling can actually be super valuable. In the United States, the disposal of electric meat grinders, like other household appliances, is managed through specialized electronic waste recycling centers. Even though meat grinders do not technically fall into the traditional electronic waste category, you can still drop them off at locations that accept small household appliances. Many cities operate special household waste collection centers that accept electronics and electric devices. You can usually find information about these programs on your local city government website. Some stores where you bought your meat grinder might also accept old appliances for recycling, depending on their policy. While not always included in official e-waste programs, some organizations will still take them in as household electrical devices. Companies that specialize in household waste management may also accept electric appliances. This service might come with a fee. Before dropping off a meat grinder, make sure to check if there are any specific preparation requirements, like removing hazardous materials. I know you have had that sneaky thought: just toss it in the garbage and pretend it never existed. Then walk into a store and pick out a shiny new grinder that will once again grace your kitchen counter. But hold up. Improper disposal of e-waste in the United States can lead to huge fines, even criminal charges. fines can reach into the hundreds of thousands of dollars. For example, in New York City, companies that illegally dumped over 1,700,000 pounds of electronic waste were fined more than $200,000. In California, breaking e-waste laws can cost you up to $20,000 per violation, per day. Some violations have even resulted in prison sentences. Executives at a company called Executive Recycling were convicted for illegally exporting e-waste and committing fraud. But why wait for the worst to happen when you can be a part of something better? Something that helps the planet and gives your meat grinder a second chance. When recycled properly, your old electric meat grinder can transform into all kinds of useful things, depending on how it is processed and how creative people get. The metal parts can be melted down to create everything from car parts and building materials to brand new home appliances. This reduces the need to mine for new raw materials and supports sustainable manufacturing. You can even repurpose your meat grinder as a decorative item or something functional. Give it a fresh coat of paint, and it could become a funky kitchen accessory or even an art piece. If the grinder has plastic parts, they can be shredded into pellets that are later used to create new plastic items. Things like packaging or even materials for 3D printing. You can also repurpose it as a shredder for other things, like old soap, turning it into usable pieces or pellets. In some cases, people modify meat grinders to process food waste, helping convert it into compost or biogas. Meat grinders are made up of nearly 70% metal, and anything made of metal can be recycled. If the grinder's housing is made of steel or aluminum, that metal can be melted down and used to make new products. In fact, according to the Bureau of International Recycling, recycled metal is up to 3 times cheaper than newly mined material. According to the European Metal Recycling Association, the global value of recycled metal reaches about 5 billion euros per year. Around the world, 275 tons of plastic are produced every single minute, making it one of the biggest sources of waste. Recycling plastic saves about 60% of the energy compared to creating new material. Some meat grinders have plastic casings or parts, and today's technology makes it possible to recycle that plastic into brand new materials. This helps cut down on resource consumption and protects the environment. At recycling plants, robotic or manual systems separate plastic components from the rest: metal, wiring, motors. Then, powerful shredders break the plastic into small pieces just a few inches in size. These shredders look like giant metal jaws that spin and grind the plastic into pellets. The shredded plastic is sent into hot water baths with special detergents, often alkaline-based, to remove grease and grime. Food bits, oils, dust, and dirt get separated. Dirty particles float, while clean ones sink. Clean particles are then dried in large drums or using high-powered air blowers. After drying, the plastic is scanned and automatically sorted by type, so it can be sent to the right recycling stream. This entire process takes just a few minutes per batch, but each facility can handle dozens of tons of plastic appliance parts every day. The motor is the heart of a meat grinder. It is made of copper and other valuable metals, and it can be recycled by extracting the copper for reuse in other devices. Electronic components are usually processed at specialized facilities that recover precious materials. Every kilogram of recycled e-waste can contain nearly 2 ounces of gold, which makes it incredibly profitable to process. The large bundles of wiring often found in household devices are made of copper or aluminum, both highly recyclable materials. Copper is one of the most recycled metals in the world, with 90% of copper wires making their way back into production. Once every single part of the meat grinder, from the big metal pieces to the tiniest plastic fragments, has been cleaned, shredded, and sorted, they get directed to special containers. But these are not your average trash bins. They are organized zones, where every type of material has a specific destination. Metal parts, especially steel and aluminum, go into large bins and are sent off for melting. They might be turned into bicycle frames, car parts, or even new kitchen appliances. Copper recovered from the motor is pure treasure. It gets shipped to specialized plants, where it is melted down and becomes part of new electronics, maybe even the smartphone you are holding right now. Plastic is ready for a new life too, as storage bins, furniture components, or even park benches. Hazardous elements, like leftover grease, paint, or circuit boards with heavy metals, are not dumped into common containers. They are sealed in special packaging and sent to facilities designed to neutralize or dispose of them safely, so they do not harm the environment. And just like that, once all the parts are sorted, your old meat grinder begins its journey into a new life. The dust settles, machines hum. On the horizon, a new device appears, maybe built from your grinder's very parts. One day, you might pull up to the park in your car with shiny wheels, sit on a plastic bench, grab your smartphone to snap a photo of a new playground and a blooming tree, and realize part of your old meat grinder lives on in everything around you. It was all worth it. Every bit of effort and time you spent recycling that old appliance paid off. And the best part, you can keep doing it. The cycle is complete. Your meat grinder did more good than some people ever will. Ever wonder where your old laptop goes after you toss it out? Every single year, millions of tons of electronics like these end up getting recycled. But hey, it is not just trash. Inside, there is a real treasure trove. Gold, silver, copper. And right alongside that, toxic hazards, mercury, lead, and batteries just waiting to burst into flames at any moment. How do they protect your data on those old drives? Why are the workers dressed like astronauts? See for yourself the shocking but super important journey your old gadget takes, from the conveyor belt all the way to extracting precious metals. It is a sight that will totally change how you think about unwanted electronics. Keep watching. Specialized companies or collection points take in old laptops from regular folks and businesses. The devices get checked to see if they still work. Laptops that are still working might get fixed up and resold, or donated to charities. Large batches of laptops are transported to specialized facilities. There, trucks unload containers full of laptops. Workers using forklifts move them to the sorting area. Then, workers wearing protective gloves and special suits look over each laptop. Yeah, safety is a really big deal here. The people on the sorting line wear protective gloves and suits for a few reasons. Old laptops might have components containing lead, like in the solder, or mercury in the fluorescent backlights of the displays. Touching these without protection could lead to poisoning. Cadmium and beryllium are dangerous if they touch your skin, or if you breathe in the dust. These heavy metals are used in batteries and circuit boards. Some laptop parts, especially broken screens, can have sharp edges that could easily cut your hands. And during disassembly, small components can break off and go flying. Even when a laptop seems dead, some capacitors can still hold a residual charge. Touching them without protection could give you an electric shock. Special anti-static suits and gloves prevent damage to electronic components from static electricity. When the laptops are shredded, a lot of toxic dust is created, which can contain microscopic particles of metal and plastic. To avoid breathing this dust in, workers wear masks or respirators. Working laptop models are set aside during sorting. They can be repaired and sold. The rest are sent off for recycling. Lithium-ion batteries are removed by hand because they can catch fire or explode. During shredding, or if they get damaged mechanically, the battery can overheat and ignite. Lithium reacting with air or water can release flammable gases. Also, inside the battery, there are toxic electrolytes that can cause chemical burns or poisoning. If a battery gets deformed, these substances can leak out and get into the environment. That is why workers manually unscrew the panels and take out the batteries. If the battery is built in, they disconnect it using a special tool. The removed batteries are placed into heat-resistant containers filled with sand or other non-flammable materials. They are stored in well-ventilated areas, away from other waste materials. Recycling the batteries happens separately from the rest of the laptop. They go to specialized plants where the metal casings are shredded. From the internal materials, like nickel, cobalt, and lithium, useful components are extracted for reuse. After the batteries, the next critical step is removing the hard drives. Why are hard drives taken out separately? Well, the thing is, even if the laptop does not work, data can still be stored on the drive. And corporate or government laptops might contain sensitive data, so the hard drives have to be destroyed following special procedures. Some drives have moving mechanical parts, like platters and motors, which are processed separately. Other drives are made of memory chips that need a different recycling technology. Workers unscrew the laptop casings and remove the drives by hand. In some models, solid-state drives are built right into the motherboard. In that case, they are either desoldered or broken off along with the board. After that, there are 3 ways they physically destroy the drives to ensure data security. They are either shredded in special shredders, turning them into tiny metal fragments, or they are wiped using magnetic degaussers, which erases the data permanently, or they are melted down into metal ingots. The aluminum casings from hard disk drives are sent off for remelting. The magnetic platters have coatings of gold, platinum, and cobalt, which are extracted using chemical processes. Solid-state drive controllers contain copper, silver, and rare earth metals. These are also extracted for reuse. Once the batteries and hard drives are out, the laptops do not pose a serious fire or data security threat anymore. Now, they can be sent over for automated case disassembly. The laptops move along a conveyor belt, passing one by one under an automated press. Powerful hydraulic plates with up to 5 tons of force squeeze the casing, causing tiny cracks in the fasteners. One hit, and the top panel separates from the bottom, leaving the internal components accessible for further processing. The laptops keep moving down the line. Mechanical arms with thin metal fingers hover over them. Each arm is equipped with an automatic screwdriver unit that spins at up to 5,000 revolutions per minute. In just 4 to 6 seconds, the robot unscrews the screws and carefully removes the keyboard, speakers, and cooling system heatsinks. When the laptop reaches the next module, 2 pneumatic grippers grab onto the screen. A blade with a high-precision control system runs along the edges, cutting through the plastic fasteners. A barely audible crack, and the display is separated. Now the laptop is almost empty, with only the main guts left, the motherboard. Another arm removes it, using vacuum suction cups to lift the board and place it into a separate container. The whole process takes less than 2 minutes, and what was once a whole laptop is now just separate parts, ready for sorting and further recycling. The conveyor moves the separate laptop parts to sorting stations. Both robots and people work here. Plastic case panels are directed one way. They pass through special scanners that identify the type of plastic. Some types of plastic can be reused. Others are disposed of as regular waste or converted into fuel for industrial plants. Metal parts, like case frames, fasteners, and heat pipes, go through magnetic separators. Ferromagnetic metals, like iron and steel, are separated using powerful magnets. Non-ferromagnetic metals, like aluminum and copper, are sorted using induction detectors. Glass from the display screens goes into a shredder, where it is broken into small fragments. After that, special equipment cleans the glass granules of impurities. The resulting material can be used to make new displays or building materials. Motherboards, graphics chips, processors, and other integrated circuits are collected separately. They are checked to see if they can possibly be reused. If the circuits are still usable, they are sent to the secondary market or for refurbishment. Most electronic components, however, end up being recycled. To do this, they are sent to special furnaces where high temperatures burn off the organic materials. Only the metals remain: gold, silver, copper, palladium. They are extracted using chemical methods, purified, and returned to manufacturing. Laptops also contain hazardous substances: lead, mercury, cadmium, lithium. These cannot be allowed to enter the environment, so they undergo special processing. The fluorescent lamps from displays, which contain mercury, are separated under sealed conditions so that mercury vapor does not escape into the air. The recovered mercury is reused, for example, in medicine or in making thermometers. The lithium batteries, which were removed in the initial stage, are transported to separate plants. There, they are dismantled, and lithium and other useful elements are extracted. The resulting materials are used in the production of new batteries. Lead, found in solder, is melted down under controlled conditions, separating it from impurities. The entire process of dismantling, sorting, and recycling a laptop can take anywhere from a few hours to several days, depending on the scale of the facility and the technological process used. After sorting, all the materials are distributed into separate containers, or large industrial bins, depending on their type and the next steps in processing. In the plastic containers, you will find fragments of casings, keyboards, touchpads, which might be black, gray, or silver. The plastic is sorted by type: acrylonitrile butadiene styrene, polycarbonate, polypropylene. In the bins for metals, you can see piles of parts. Here lie aluminum frames and lids from laptop cases, copper heat sinks and wires, steel fasteners and screws. Containers for electronics are filled with the removed motherboards, graphics chips, random access memory modules. It all looks like a heap of complex green and blue boards with gold contacts and copper traces scattered across them. In separate containers for displays, there are dismantled screens with fragments of glass and metal frames. Sealed containers for hazardous materials hold batteries. Mercury lamps and capacitors containing lead are stored separately. These are often kept in special zones with warning signs about toxicity and explosion risks. After sorting, all these materials need to be transported to specialized plants where they will undergo further processing and preparation for reuse. To save space in trucks and containers, some materials are compressed. For example, plastic is shredded into granules or pressed into large bales. Metals are compressed into dense cubes. Glass is crushed and packed into bags or containers. Electronic components are stored in large containers without being compressed, since they still need to undergo chemical treatment. Lithium batteries are placed in special non-flammable containers, often filled with sand or expanded clay pellets to prevent ignition. Mercury lamps are transported in sealed boxes that prevent mercury vapors from getting into the air. The materials are loaded onto trucks, trains, or ships, depending on the distance and the type of material. Large metal cubes are lifted by forklifts and stacked in trucks. Containers with plastic and glass are transported in trailers or sea containers. Electronic components might be transported in special containers with shock-absorbing protection. Metals are sent to metallurgical plants, where they are melted down and purified. Aluminum, copper, and iron can be reused in manufacturing electronics, cars, or building materials. Plastic goes to plastics recycling plants, where it is shredded, melted down, and used to produce new casings for electronics, furniture, or packaging. Glass goes to facilities that manufacture new screens or building materials, for example, insulation made from recycled glass. Electronic circuit boards are delivered to plants specializing in extracting precious and rare earth metals. There, the integrated circuits are dissolved in chemical solutions to extract gold, silver, palladium, and other valuable metals. Batteries head to facilities where lithium, nickel, and cobalt are extracted for manufacturing new batteries. Hazardous waste goes to special landfills or chemical plants, where toxic substances are neutralized or rendered harmless under controlled conditions. After several months or even years, the materials from a recycled laptop can end up back in production, as part of a new device, building, or car. Some large recycling facilities specialize narrowly, for example, dealing only with computer equipment or mobile devices. Others recycle almost all types of electronics, including large household appliances. Every year, the United States spends $17 billion just on importing fresh fruits, and avocados from Mexico alone rack up $3 billion of that. The sugar in your cup of tea? Chances are, it traveled thousands of miles from Latin America. Americans chow down on 1 billion pounds of tuna every year, and 90% of winter tomatoes come from Mexico, where agricultural cartels are battling it out for control of that market. From olive oil out of Spain to turmeric from India, imports keep the United States fed with variety and savings. In this video, we're going to spill the beans on where your favorite foods come from, the numbers behind their journey, and why it matters to every single one of us. Don't miss it. It's going to be tasty and full of surprises. Get comfy. Brew yourself some tea. Do you take it with sugar? Well, that sugar probably came from another country just for you. Even though the United States produces its own sugar, demand often outstrips supply, making imports a must. The United States is a huge sugar consumer. Plus, producing sugar in some countries is cheaper thanks to better climates and lower costs, which makes importing a smart move. The big players supplying sugar to the United States are countries in Latin America and the Caribbean, especially Mexico, which gets a sweet deal on the American market thanks to the North American Free Trade Agreement. Closing some borders in 2025 wasn't meant to mess with legal trade between the United States and Mexico. Still, it might have slowed down logistics and caused delays in getting goods like sugar across. The European Union is a key supplier of seafood to the United States of America, keeping the American market stocked with all kinds of fish and shellfish. This helps meet demand for seafood in the United States and keeps the supply steady. Spain and Japan are major players when it comes to fresh and frozen tuna for restaurants. Tuna is one of the most popular seafoods in the United States. Americans eat about 1 billion pounds of it a year. That makes the United States one of the world's top tuna consumers. Thailand, Indonesia, and Vietnam are the go-to sources for canned tuna, the most affordable and in-demand option. You'll find it in salads, sandwiches, or just as a quick snack. French oysters and other shellfish are a hit with American eaters too. The Netherlands pitches in with fish shipments to the United States as well. Every year, the United States shells out more than $17 billion just on fresh fruit imports. The biggest supplier? Mexico, covering over 40% of all fruit imports to the United States. Importing means supermarkets can offer a huge variety of fruits no matter the season. Americans eat more mangoes, pineapples, and avocados than they can grow at home. Plus, bringing them in from countries with cheaper labor often beats growing them domestically. Take avocados. Mexico supplies over 90% of the avocados imported to the United States. Each year, Mexican farmers ship over 2,640,000 pounds of avocados to the American market, worth about $3 billion. Most of those avocados come from Michoacán, where the climate's just perfect for growing them. Every year, the United States imports over 880,000 pounds of olive oil, costing around $1,500 million. Demand's climbing thanks to the Mediterranean diet craze and the push for healthy eating. Drop a comment below. Do you go for healthy eating too? Meanwhile, American producers, mostly in California, are trying to ramp up their own olive oil output, but it's still a drop in the bucket compared to Europe. Spain leads the pack, supplying over 40% of the olive oil imported to the United States. Spanish oil's a favorite for its quality and decent price. Italy, which used to rule the American market, now sits in second place with about 30% of imports. Greece and Tunisia are stepping up too, especially in the premium oil game. The most popular cheese in the United States? Mozzarella. It makes up about a third of all cheese eaten here, thanks to being the star of pizza, one of America's favorite foods. Cheddar's a close second, showing up in sandwiches, burgers, and mac and cheese. The United States churns out over 13,200,000 pounds of cheese a year, but it still imports premium kinds too. Top suppliers include Italy, France, the Netherlands, Switzerland, and Spain. Each year, the United States brings in over 352,000 pounds of cheese, worth about $1,500 million. Most of it ends up in restaurants and gourmet shops since real European cheeses cost a pretty penny here due to tariffs and shipping. Parmesan's a big name and a fan favorite in the United States. The country imports over 22,000 pounds of it yearly, though a lot gets used pre-graded. The real Parmigiano Reggiano is pricey, so the local knockoff, Parmesan, made with simpler methods, is way more popular. 70% of tomato imports come from Mexico. Mexico supplies nearly 100% of the fresh winter tomatoes in the United States since its climate lets them grow year-round, while American production tanks in the cold months. US farmers grumble about cheap Mexican tomato imports, and trade spats between the two countries have flared up more than once. Most of those tomatoes roll in through Florida, but they compete hard with local ones, putting political heat on the US government to cap imports. Texas border crossings handle millions of tomato crates every year. For example, over 50,000 trucks loaded with tomatoes pass through Laredo alone annually. Mexico sends over tons of cherry and Roma tomatoes, loved by Americans for their sweetness and cooking convenience. Oh, and in Mexico, powerful agricultural cartels run the tomato show, sometimes sparking criminal showdowns over market control. Canada's the third biggest food supplier to the United States, trailing only Mexico and the European Union. What do you think? Could we lose such a major importer anytime soon? Key categories include meat, grains, dairy, fish, and veggies. Canadian pork exports to the United States top $2 billion a year. Canada's also a big beef supplier, especially after mad cow disease caused some hiccups. But chicken? Nope, Canada's not sending that over. A bird flu outbreak wiped out poultry and slashed egg supplies big time too. Being right next door, Canada cuts down on shipping costs for the United States. Plus, their quality standards match what the American market demands. China sends a hefty chunk of food to the United States, though it's a smaller slice of their imports compared to electronics or clothes. China's a top seafood supplier, especially tilapia, shrimp, cod, and canned fish. It's also the world's biggest garlic grower, and a lot of that heads to the United States. Then there's green tea, black tea, and honey coming over too. Americans love Chinese rice noodles, sweet potato vermicelli, and wheat noodles. Demand for Asian foods has shot up over the last few decades, thanks to Asian restaurants, street food, and the healthy eating trend. Rice and sweet potato noodle consumption in the United States is up 20% in the last 10 years, driven by the gluten-free craze. The United States is one of the biggest importers of Indian spices. Top picks include turmeric, cardamom, cumin, coriander, chili pepper, and cloves. India produces over 80% of the world's turmeric, and a big chunk of that lands in the United States. Oh, and India is the second largest tea supplier to the United States after China, with faves like Assam, Darjeeling, Nilgiri, and masala chai. India is the main source of basmati rice for the United States too, perfect for healthy eaters and Indian food fans. The United States brings in tens of thousands of pounds of legumes from India yearly as vegetarian diets catch on. Mangoes? A total crowd pleaser. India ships over 33,000 pounds a year. Demand for Indian goods is booming thanks to healthy eating trends, exotic flavors, and the rise of Indian cuisine in the United States. You might wonder, why all this importing? Doesn't the United States grow broccoli or spinach? Sure, but don't forget those harsh winters in some regions. Imports dodge seasonal shortages, keep prices down, and bring variety. In summer, California, the United States' veggie powerhouse, has huge harvests, but winter cuts production way back. Cheaper labor abroad helps too. Growing and freezing veggies in places like Mexico, China, or Peru costs less than doing it in the United States. It's easier to ship frozen veggies over. They last longer and keep their nutrients, making them perfect for restaurants and big stores. Take broccoli. It holds on to its goodness when frozen. It's a legit superfood, packed with nutrients and proven health perks. Even though the United States is a top tofu exporter, it imports plenty too to meet demand. About 1,585 importers bring tofu into the United States, keeping the market stocked with options. Tofu imports have doubled in recent years. Made from soybeans, it's a protein-packed powerhouse. Tofu's a big deal in global trade, thanks to its nutrition and appeal to all kinds of eaters. The United States plays both sides as a major exporter and importer, showing how much Americans crave it. Beyond foodies and health nuts, athletes and bodybuilders dig tofu too. It's clutch for building and recovering muscles.